Welcome to lecture number 17 of PH 4105, Advanced Mathematical Physics. As you all know, we are studying differential geometry at this point, and we have come to a stage where we can introduce our next big player on the scene. These are covectors, dual, two vectors, and differential forms. Before we introduce them, however, let us just take a quick recap of what we know about vectors, whose duals these are. So tangent vectors is something we have been talking a lot about over the last few lectures. They essentially are maps which act on functions linearly to produce numbers. Not just linearly. The basic point is Vp, a tangent vector at a point P, acting on the function f, will definitely give you a real number. But what is also very important is that this is linear, as we have already said. But in addition to this, you have this derivative property, that is Vp acting on a product of two functions, f times g, gives you the value of f at the point P times value of Vp on g, plus g at the point P times the value of Vp acting on f. And it is this derivative property which clearly tells you that this vector is actually located at a point P of the manifold, because the values of the functions that are being picked up are the values precisely at that point. Now, we already know that the set of all tangent vectors at P, something which we denote by TPM, is a linear vector space. We have discussed this in great detail in earlier lectures. And the important thing is, of course, in order to be a linear vector space, you have to define addition of vectors. In fact, linear combination of vectors. And the way we do this is the following. The linear combination of two vectors Vp and Wp with real numbers a and b is defined to be another tangent vector, which of course is a map which eats up functions and gives you real numbers. So in order to completely specify this vector, you have to tell me what this map does to an arbitrary smooth function on the manifold M. And the definition which is used here is simply this, that this map acting on the function f gives you a times the value of Vp on f plus b times the value of Wp on f. That this resulting map is a map from functions to real numbers is obvious. That it is also linear and has the derivative property which tells us that this is really a tangent vector at the point P are things that we have already proven in earlier lectures. Now let us turn to the issue of one forms or dual vectors. Now, if you have done a bit of linear algebra before, you would know that dual vectors are essentially maps which map vectors into numbers. Here, you can see that you already have a way in which vectors get mapped onto numbers. Actually, we have been saying this the other way around. VPs, the tangent vectors, are seen as machines which turn functions into real numbers. But if we reverse the role and think of f as producing numbers from Vp, that can be a promising avenue to look at. Now, the function f is supposed to take a point P on the manifold and return a real number. And this function, of course, may or may not be linear. So when we are looking for something which changes tangent vectors linearly into numbers to get dual vectors, we don't really directly say that it's the function which is acting on Vp, but we invoke something slightly different but very similar. We talk about what is called a differential of a function. Okay, let me now define the differential. So, we start with a function f which is a smooth function on the manifold M, that is a member of C infinity M. We define the differential of f at a point P, denoted by dfp, to be a map which acts on TPM, the set of all tangent vectors at the point P, to produce numbers in the following manner. DFP acting on a vector VP is defined to be the value of VP, the tangent vector, acting on the function f. Since VP is a functional which returns real numbers from functions, it's easy to see that the right hand side here is a real number. So DFP definitely maps a vector to a real number. That is, it's a map from the set of all vectors, tangent vectors at the point P, to the set of real numbers. What is important is this is not just a map from TPM to R, it's also a linear map. And that's very easy to see from this definition. Note that DFP acting on a linear combination of the vectors is simply, according to this definition, the same linear combination of vectors acting on the function f. And by the definition of linear combination of vectors that we had mentioned just a while ago, this is given by A times VP acting on f plus B times WP acting on f. But now, A times VP on f is the same as A times DFP acting on VP. Note that is the definition of DFP. And here, WP acting on f is the same as DFP acting on W. Therefore, what you get when DFP acts on AVP plus BWP is a linear combination of what you get when DFP acts on VP and WP separately, weighted by these same constants A and B, same real numbers. So, what we have managed to prove is DFP's action on the tangent plane is a linear action. It's a linear map from TPM to real numbers. And this tells us that DFP is a member of the dual space TP star M, the set of dual vectors to those in TPM. Now the notion of dual vectors and the dual vector space should be pretty familiar to any one of you who has done a course in linear algebra. But just in case you haven't really come to that in your studies, I will give you a brief recap of the basic idea of dual vector spaces. Given a real vector space V, the dual space V star is, as I have just said a while ago, the set of all linear maps from V to R. So, any f which belongs to V star is a map from V to R, which has the following property that for any small v and small w belonging to the vector space capital V, and for any a and b, which are real numbers, you have the following. F acting on AV plus BW is A times f of V plus B times f of W. As we have just established, our differential of function f at a point P, DFP, has this very same property when it's acting on tangent vectors at the point P. Now, the fact that V star is a vector space in its own right follows from the fact that it can obey all the defining properties of linear vector spaces, provided you define how to add two vectors and multiply a vector by a real number. And this is done using a very simple and obvious idea. F plus G acting on V is defined to be the value of f of V plus G of V, and AF is defined to be a linear map which, when acting on V, returns to you A times f of V. Of course, from the definition itself, it's obvious that both of these resulting objects, f plus G and AF, are maps which act on vector space V and produce real numbers. What you really need to check is that these are linear maps. The proof of that is really rather trivial, so I'm not going to go into that right now. You should actually check out for yourselves that these objects that we have defined here are actually linear maps. Now, as we have claimed, V star is a real vector space under these definitions. You should check out for yourselves that all the basic defining properties of a vector space, commutativity, associativity, existence of an additive inverse, additive identity before that, etc., all of them work for V star. Now, the really important result for us is this. If V, the original vector space, is a finite dimensional vector space with dimension n, then V star is also finite dimensional. Not only that, it has dimension exactly equal to n. The proof for this hinges on choosing a basis for capital V. This basis can be any basis that you choose, V1, V2 up to Vn. There are n elements in this basis because we are talking of an n-dimensional vector space. What we are going to do is we are going to consider n elements of V star, n dual maps, phi1 through phi n. Note that I have deliberately written the 1 to n here as an upper index. These are of course not powers, these are just superfixes to sort of contrast with the basis choice that we have made for capital V, where we have used the index running from 1 to n as a suffix. Now, the way in which we define these phi i's is the following. Phi I acting on Vj is defined to be delta Ij. In other words, phi 1 acts on V1 to give you 1, but acts on V2, V3, V4 up to Vn, all the other vectors in the basis to give you 0. Similarly, phi 2 gives you 1 only when it's acting on V2, acting on all the other basis vectors it gives you 0, and so on. Now this set that we have just now defined, this set of n vectors phi 1 through phi n defined in this manner, turns out to be linearly independent. It's very easy to see that this is linearly independent because if you start with a linear combination of these which add up to 0, what that will mean is that this, when it acts on any vector, will give you 0. In particular, when it acts on the basis vectors v1, v2, vn, in general any vi, you are going to get 0. But what happens when you apply this combination on vi? Well, phi 1 acting on vi will give you 0. Phi 2 acting on vi will also give you 0. Assuming, of course, that I is neither 1 nor 2. In general, all of these phi j's acting on vi will give you 0. The only exception will be phi I itself. And that will give you 1. And that's multiplied by ci. And so, what you have on the left hand side here is nothing but ci. Since this null dual map has to give you 0 on all vectors, it gives you 0 on vi, and hence ci has to be 0. This means that the only way you can get a null combination out of this is by choosing each and every one of the coefficients to be 0, because vi could have been any one of v1, v2 up to vn. And that exactly is what we mean by linear independence. The only way to get a 0 combination of the vectors is by choosing 0 coefficients. The next point that we need to prove in order to show that this set that we have got is actually a basis of V star, and hence complete the proof that V star is n-dimensional, is to show that this set spans V star. That is, every element of V star, every dual map which maps capital V into R linearly, is actually a linear combination of phi 1 to phi n. The way we show this is the following. Let us choose an arbitrary function f on V star. This is of course an arbitrary linear map which acts on vectors to produce numbers. In particular, acting on the basis vectors v1, v2, v3 up to vn, it produces n numbers. F of vi, that's how we define our numbers fi, f1, f2, f3 up to fn. Now, we consider a particular linear combination of these phi i's. Fi phi I. Remember, Einstein's summation convention is enforced. If you have a suffix and a superfix repeated, you are going to assume that they are summed over all possible values which I can take. In this case, from 1 to n. So, Fi phi I is nothing but f1 phi 1 plus f2 phi 2 all the way up to fn phi n. Now, let's take this Fi phi I and apply it on Vj. Fi's, remember, are numbers. and the way we have defined multiplication of a dual map by a number, and the way in which we have defined the addition of dual maps, tell us that this is the same as Fi times phi I Vj. Note that this is not just multiplication of a dual map by a number, there's also an addition involved. So you really need both of those to write this down, but that's sort of obvious. But phi I Vj is by choice delta Ij. And when you carry out this sum over all I, of course the only term which survives is Fj, all the others are multiplied by 0 here in the sum. So you get Fj, which is nothing but f of Vj. So Fi phi I, this linear combination, returns exactly the same value as f does on each and every one of the basis vectors. Now, from here it's obvious that Fi phi I will return exactly the same value as f does on any vector, because every vector after all is a linear combination of the vi's, and f acting on any such linear combination will give you a linear combination of values it produces on the basis vectors. Since Fi phi I gives you the same values on the basis vectors, it will definitely give you the same value as f does on any vector. And this means, of course, that f is nothing but exactly Fi phi I. In other words, give me any map f which belongs to V star, you can find the linear combination of the phi i's which will give me exactly f back. So, phi 1 to phi n spans V star. Of course, I have made a mistake in here. I have written phi 1, phi n as suffixes. They should have been superfixes. I just checked that I had written them correctly as superfixes earlier. So, let's just ignore that and go ahead. What we have just shown is that this set phi upper 1 up to phi n is both linearly independent and spanning, so it is a basis of V star. These are the basic facts that we will need about the dual vector space to any vector space. Let us now return to the vector space that interests us the most right now, which is a tangent plane to a manifold at a point P. The set of its duals, Tp star m, the set of all linear maps from Tpm to R, of course, must exist, and we have already seen that it's not empty, in the sense that we have seen examples of members of Tp star m. DFP, the differential of a function at a point P, that we have discussed at the very beginning of this lecture, is actually one such dual vector. Tp star m is the set of all dual vectors, not just differentials of functions. Now, elements of Tp star m are called covectors, as opposed to vectors, which are of course elements of Tpm. Now, covectors is a comparatively recent terminology. Earlier usage was to call these things covariant vectors. And according to this usage, tangent vectors were actually called contravariant vectors. Contravariant and covariant, these two terms used to be pretty common, and they are still pretty common in physics circles. However, the name covariant vector and contravariant vector sort of confuses people a bit. Contravariant means to transform in an opposite manner. Opposite to what, one might ask? After all, a vector transforms like a vector. And this stress on variation, change when you change your coordinates, is central to the physics definition of vectors. However, as we have seen in these lectures, the transformation rule which a vector obeys is a natural property of its basic definition, whether it be the geometer's definition as a germ or an algebraic's definition as a linear map with a derivative property. So, the name covariant is not really that much in vogue nowadays. Physicists, of course, cling to habit a lot. So in physics texts, you are going to see the term covariant vectors used quite often. We are going to call them covectors, although I must confess that I might also slip into the habit of calling them covariant vectors from time to time. As for contravariant vectors, we are just going to call them vectors. Except, again, sometimes, out of the force of habit. Now, the name that we give to Tp star m should also be pretty obvious here. TPM is called the tangent plane at the point P. Tp star m, in accordance to the fact that its elements are covectors, is called the cotangent plane to M at the point P. Now, as we have just seen, a dual space to a vector space is finite dimensional if the original vector space is. Not only that, it has the same dimension as the original vector space. So, for an m-dimensional manifold, we have already seen that TPM is an n-dimensional vector space. So, Tp star m is also an n-dimensional vector space. Of course, we have to define how to add cotangent vectors or covectors here. And that's pretty easy. All you do is define it exactly the same way that we did for general dual maps. A alpha p plus b beta p is defined to be that cotangent vector which, when acting upon a tangent vector Vp, gives you A times alpha p acting on Vp plus b times beta p acting on Vp. This is true for all A and B, all real numbers and all Vp. And of course, for any alpha p and beta p, these two members of Tp star m, this is going to work. Now, just like we had a tangent bundle, which is a union of all the tangent planes to the manifold, if you take the union of all of them, collect them all together, you get the tangent bundle. Similarly, if you collect all the cotangent planes, all of these Tp star m's for every p together, that is, take their union, you are going to get the cotangent bundle T star m. By the way, we had already talked about the connection between the tangent bundle and classical mechanics. At least we have alluded to that in the terminology that we had used there. At least for the induced charts, we had talked of QIs and Q dot Is in analogy with what we did do in classical mechanics. That is basically because the tangent bundle plays a hugely important role in classical mechanics, where M would be the set of all possible configurations of the system. T star m is perhaps an even better known bundle in classical mechanics, because T star m is exactly what we call the phase space in classical mechanics. We are going to discuss this in great detail later, but I just thought that I would point that out to bring the connection to physics even closer. Now, just like once you have a tangent bundle, you can talk about vector fields. Now that we have cotangent bundles, we can talk of covector fields. So a covector field alpha on a manifold M is defined to be a map from M to T star M, this cotangent bundle, which assigns to each point P of M a covector. Alpha at the point P is alpha P sub P. The same kind of notation that we use for value of a vector field is being used here. But this alpha P is a member of Tp star M. Note that just like tangent vectors are stuck to a particular point, covectors are also stuck to particular points on the manifold. And what this alpha does is that it's not just a map from M to T star M. Acting on a point P on M, it doesn't give an arbitrary element of T star M. It gives you a covector which is stuck to the point P on which this alpha is acting. Now, a covector field, alpha, acts on a vector field X just like a covector acts on a vector. When a covector acts on a vector, you get a number. Of course, the covector at a point P has to act on a vector at the same point P. Here, when a covector field alpha acts on X, what it returns is a function whose value at a point P of the manifold is defined to be. This is of course a definition of alpha acting on x. This function is defined to give you the number which is the value of alpha p, alpha at the point p, acting on capital XP, the value which the vector field takes at the point p. So given a covector field and a vector field, the action of the covector field on the vector field is simply the following. At every point p of the manifold, you find out the value of the covector field, which is a covector, find out the value of the vector field, which is of course a tangent vector at that point, and you make the covector act on the vector, and that returns a number for a particular input point of the manifold. So this ultimately is a map from M to R. Now this map is not guaranteed to be a smooth or differential map or anything at this stage. We are just talking about a map from M to R. So this action alpha x of a covector alpha on a vector field x is very useful, and we keep on referring to it several times. We can often use other notations for it depending on the book you're reading. For example, some people might write x comma alpha within angular brackets to denote the same thing, to sort of suggest that it's somewhat like an inner product, if you know what I mean. Frankly, we are not going to talk about inner products right now. We are in no position to do that at this stage of our discussion. Another notation that's often used is x with this, I don't even know what the symbol is called, x and this inverted L alpha. Regardless of what the symbol is called, this operation is called a contraction or an interior product. Now, very often we are going to deal with a large number of covectors acting on vectors, acting on points and so on. As you could see from the expression that you have just written down, the definition of alpha of x itself, there are plenty of brackets in this picture, and sometimes the number of brackets becomes intimidating, and at least, unless you are very, very careful, somewhat confusing. Using notations like angular bracket x comma alpha or x with this symbol, whatever that is, alpha, sort of allows you to get rid of a lot of these brackets and makes life a lot easier sometimes, which is the reason why we often use these notations. Now, this fact that a covector field acts on a vector field to produce a function on the manifold gives us a perfect way to define smoothness of covector fields. Let me remind you that a vector field acting on a function gives us a function, and we defined a vector field to be differentiable or smooth if whenever it acts on a smooth function, it returns a smooth function. Now, given the fact that we already know how to define smooth vector fields, this definition of alpha acting on x to produce a function helps us to define a smooth covector field simply by saying a covector field is differentiable of class C infinity, or in other words, smooth, if acting on every smooth vector field x, and x which is a member of this set of all smooth vector fields, produces a function which is infinitely differentiable or smooth. So a covector field is smooth if acting on any smooth vector field, it produces a smooth function. Now, these smooth covector fields are actually very, very important in both differential geometry and physics. And they have a special name. They are the so-called differential forms or one forms. The one in the name indicates that there would be other higher order things like two forms or three forms, which we will discuss later. But for the time being, let's just focus on one forms. So they are just maps which map vectors linearly into numbers, or rather the values of the covector fields at a point is a map which maps vectors linearly into numbers. And so the covector field as it stands maps vector fields into functions, and a smooth covector field, something which maps a smooth vector field into a smooth function, is exactly what we call a differential form or a one form. I'm repeating this because this is a very, very important definition, and we will meet one forms several times in the times to come. Both one forms and their higher order cousins. Now, the set of all differentiable covector fields, the set of all these 1 forms, is denoted by lambda 1m. The 1 on top here indicates that we are talking about 1 forms, and of course later on when we talk of 2 forms, the set of all 2 forms will be denoted by lambda 2m and so on. Now covectors at a point form a vector space, the dual space to the tangent plane that we have seen before, something that we call the cotangent plane. What about covector fields? Now covector fields can be linearly combined in a very simple manner. You can define the sum of 2 covector fields alpha plus beta to simply be something whose value at the point P is alpha P plus beta P. Remember, we have already defined before how to add 2 covectors by essentially saying that acting on a vector at a point P is going to produce the sum of the individual results of the actions of the covectors. So we know how to evaluate the right hand side and get a covector at the point P. Alpha plus beta simply gives at point P alpha P plus beta P. Similarly, you have something akin to multiplication by a scalar, f times alpha at P, where f is a function, gives you f of P times alpha P. Now under this set of definitions, lambda 1m forms what is called a module. This is like a vector space, but with one major difference. A vector space is a space under a field. Typically, in most of our applications, we talk of the set of all real numbers or the set of all complex numbers, depending on what kind of vector space you're talking about. However, the set of functions, though very similar to fields in many ways, these fields of numbers, there is a major difference there. In a field, you should be able to divide by every element which is not the additive identity. That is, everything which is not 0, you can divide by. That definitely is true for real numbers. That's also true for complex numbers. However, when you're talking about the set of functions, the additive identity is of course the function whose value is 0 everywhere. And definitely you cannot divide by that. But the important point is, in the set of functions, there could be other functions which are not identically 0, but which are 0 at 1 or more points. You are not allowed to divide by them either to produce resulting functions. So, in the set of all functions, things are somewhat like the set of numbers, with one major exception. You cannot have a multiplicative inverse for every non-zero element. As a result, the set of all functions, in this case the set of all smooth functions, C infinity m, is algebraically a ring and not a field, and the corresponding thing where you essentially have a vector space like behavior but not with a field but with a ring, forming the so-called scalars, what you have is what mathematicians call a module. So lambda 1m is really a module. Now we will end today's video by talking about a very special and important 1 form. Remember, that's a smooth covector field. Now we have already met its point-wise version before. Very first example of a covector that we talked about was differential of a function at a point P. Now given a function f which belongs to C infinity m, a smooth function, we can define a covector field df, which is also called the differential of f. Note the difference in nomenclature here. dfp is a differential of f at a point P, and df is simply the differential. This is a covector field which is defined at the point P. Well, no marks for guessing what the definition is. df at the point P is simply defined to be the value of dfp. Now, is this a smooth covector field? Let's check. Well, you have to figure out what function you get when you apply df on a smooth vector field capital X. To figure that out, all you need to do is figure out its value at the point P, and that by definition is the value of df at the point P acting on X at the point P, that is dfp acting on SP. And by our definition of the differential of a function at a point, there is nothing but xp eating up the function f and producing a real number. And this, by the way, is nothing but xf acting on P. This is a definition of the function xf, the function you get when a vector field acts on some function f. But remember, because we have a smooth vector field x, its action on any smooth function f has to be a smooth function. So this dfx, this function, which is the same as xf, because of course it returns the same value at the point P, both of these do, we have this result that df acting on a smooth vector field always produces a smooth function, and therefore df is a smooth covector field or a one form. Now, what does this d do here? The d actually changes the function f to a one form, a smooth covector field. Now, this differential operator is going to play a very important role, and later on we will see that you can also define its variants which act not on functions but on one forms to produce higher order things called two forms. There's another version for two forms which produces three forms and so on. But that is something we have to discuss later. For the time being, let me stop here today. We will talk about more properties of differential forms and covector fields in general, especially how to represent them using coordinates, how do their components change when you carry out a coordinate transformation, or rather go from one coordinate patch to another, and similar issues. Bye till then.